Welcome to the Parallel Programming Project Notes. Now, why are these notes even here? To help you get a better grade, better grade, better grade, better grade. You're going to be turning in projects, okay? We're going to tell you in this note set how to do it such that you don't lose points for silly reasons. Okay, so first of all, feel free to run your projects on whatever systems you have access to. I think a lot of the projects are easiest if you run them on our Flip servers here at Oregon State. But if you have your own system, you can certainly use it, and I will help you as much as I can get the code up and running on your system. If you're on campus, well, you have access to the Linux systems, log into Flip, or Windows systems. There's Windows systems scattered around the College of Engineering. eCampus users, we don't have remote access into the Windows systems, as far as I know, other than maybe Citrix, but you will have the same access to the Linux systems. We have another system called Rabbit, which looks very much like Flip, and it was bought just for this class. So that's not a bad system to be on too. In theory, you're not competing with people from other classes. For GPU projects, yes, you will have access to GPU systems here running Linux. And for the multiprocessor projects, you will have special access to that as well. This is the cluster system. The projects will require timing. We're going to be doing benchmarks. If you set this parameter to this, it runs at a certain speed. If you set the parameter to this, does it get faster? Does it get slower? If so, by how much? And so we have to do timing. In OpenMP, this is a function to tell you what the precision of the clock is. And if you run this on Flip, it'll tell you that it's a nanosecond. I find that hard to believe, but that's what it says. And then this is the click the stopwatch function call, like how many seconds since the program started, okay, which you'll probably turn into milliseconds or microseconds. Anyway, we'll talk about that later, but this is what you'll be doing. Now, again, we don't want to just implement, we want to characterize the performance. If you click that stopwatch twice so you get a delta time, well, that's in seconds. This would be in microseconds. And then when you go to print it, a lot of these timings, because there are so many decimal digits down, we're going to make them in double precision. And if you print double precision in %F for float, it won't work. If you do it in %D, which a lot of people think means double, it'll work even worse because %D is not double, it's decimal integer. For printing double precision numbers, it's LF, long float. So remember this. Make a note of this. When we get to the point of trying to print out double precision numbers, it's LF, long float. How reliable is the timing? Well, again, I don't know what the precision of the clock really is, but a lot of times you're at the mercy for how loaded the system is because you're sharing clock cycles with everyone else. The way you can find out if you're on Linux, like Flip, you type uptime. And uptime, well, it's really there to tell you how long since the last crash, but these three numbers are really important, okay? This is the system load average for the last 1 minute, the last 5 minutes, and the last 15 minutes. If these numbers are big, like 10, 12, 15, don't run your timing test. You're going to get sucky results. If they're 3, 2, 1, that's kind of nice, then do run it. You will get pretty nice results. Okay. Now, here's what we're going to do for the timing. And what I recommend is you run the test multiple tries. Okay. And each time you're looking at the performance, in this case, megaflops. So you're going to compute megaflops and you're going to keep track of what the maximum megaflops is. And so you're going to run this some number of tries. I typically use like 20, and you're going to keep the maximum performance. You're not going to average them. You're going to keep the maximum one because that's the one that was probably the least impeded by other people running programs. You also are going to compute an average. So you're summing these and then you're dividing by the number of trials, the number of tries, and you compare the peak performance against the average. And so if you get something like this, okay, 1.1 or 1183 megaflops, and then but your average is 1141, that's pretty good because that means that all of the numbers necessary to produce that average were right around the maximum performance. So that's a reliable result. This is not a reliable result. These are both examples from things I ran. 600 megaflops is the peak, and less than half of that is the average, which means there was one really good run, and then the rest were kind of down here, and some higher and some lower. But it means there's a lot of variation, and so you don't really want to trust what you get. Okay, so here's a trick you can use to try and get better numbers. The better numbers, the more reliable numbers you get, the better your graphs will look, the more insightful your graphs will be. Okay, if you're on Linux, you're going to use G++. Okay, if you have access to the Intel C compiler, go ahead and play with it, but don't use it for your final benchmark results. And the reason is, and this is going to sound weird, ICPC is too good. And it is my experiences with this compiler is it is so good that it will remove parts of your code it thinks you don't need for you without telling you. Well, that's what benchmarks are, right? Benchmarks are computing for the sake of computing. And so there are pieces of your code that the ICPC compiler might decide, you know what, this chunk of code doesn't actually accomplish anything. I will delete it, and which really screws up your results. So you play with ICPC if you've got it. It's interesting, but take your numbers with G++. Okay. Many of these projects will require you to submit graphs. Let's set the convention right now that for performance, up means faster. Okay. So that means you're going to plot something like megaflops. So that more megaflops means faster. Do not plot something like elapsed seconds because in elapsed seconds, up means slower. Okay. We always want up meaning faster. That way we can look at each other's graphs and have a good sense of what they're telling us. Also, I expect your graphs to show off scientific literacy. Come on. It's called computer science. The science is in there for a reason. Okay, I expect axes to have numbers and labels and units. If there's multiple curves on the same set of axes, I expect that I can tell which is which. You know, little lines drawn to them or colored something or a legend. Okay, this is a way to lose points. Don't do it. Common Linux commands. Yep, if you're less familiar with Linux, these are the ones you really ought to know. They're the ones you use all the time. Diverting to a file, and we'll talk about this as we get started, but if you really, really, really want to save some time, of course, you could print out the numbers from your program, and then you could type them all back in again into a spreadsheet. Or you could, on Linux, run it, say greater than, and a file name. And that will take the results and just stick them here so you don't have to retype them. You probably should say greater than ampersand. That grabs both standard out and standard error. But CSV is comma separated values and it's a format accepted by Excel. So if you output your file from your program in the right format and put it in a CSV file, you probably can just double click on the CSV file and poof, there go all your values right into Excel. Again, only if you want to save time. If you want to do it really long and laboriously and have it done in a couple of hours instead of 5 minutes, that would be fine. That's up to you. All right, standard output, standard error. Printf goes to standard output. Printf standard error goes to standard error. Both of these appear on your console. So what's the difference? You'll see in a lot of the sample code, I like printing to standard error. Standard error is unbuffered, meaning if I print one character, the system sends that one character out and you see it. Whereas printf is a lot smarter. Printf buffers it. So it writes it into an internal buffer and then eventually flushes the buffer. But if your program crashes, that buffer for, for printf doesn't get flushed. And so you might have some crucial message sitting there that will give you a clue why your program's crashing, but you don't get to see it. Whereas standard error, you get to see everything, even if your program crashes. So yes, you will see this all through the sample code. I like printing to standard error, which means when you divert to a file, you want to use this greater than ampersand. That says take both standard output and standard error, send them to a file. All right, computing performance. If you're multiplying big numbers, like you have some number of samples and you want to compute samples squared, be careful of overflowing an integer. Okay. If num_s if it's a signed integer and num_s is bigger than 46,000, you'll overflow the integer. If you're doing unsigned and num_s is bigger than 65,000, you'll overflow the integer. If you have to multiply two integer quantities, you might do this. Float them. That way you don't accidentally overflow. If you overflow an integer and then you use it in performance calculations, it gives you very strange results. Wrong ones. All right, project turn-in. All projects will be turned in on Teach. teach.engr.oregonstate.edu. Hopefully you've used it before. Turn in all your source files. That could be a CPP file, could be an OpenCL file, could be a CUDA file. Okay, you don't need to turn in the executable of your programs. Or we'll assume you actually ran it. And then the other thing you'll turn in is a report in PDF format. Okay, the PDF report will include a bunch of title stuff, so we know whose it is, tables or graphs, and an explanation. What patterns are you seeing in the graphs? Why is it that way? Why is it looking that way? Okay. Now, what happens is I've got a script that goes out to Teach and vacuums up all of your submissions. And then I concatenate it into one big PDF, and that's what we grade from. So if you forget to put your name on the top of the first page, we won't know whose we're grading. We'll just get to the next page in the big PDF file, and there will be no name there. And we can't give you credit for the points you earned because you didn't put your name there. Put your name there. Bonus days. If you've been with me before, you understand this already. But if you haven't, this is pretty easy. You all have been given a gift. Here it is, of 5 bonus days. And a bonus day is a no questions asked 24-hour project extension. I don't care why you're taking it. You're not feeling well, you have a conflicting project due from another class, any reason. But you've got 5, and you can only use 2 at a time, 2 on any given project. Okay. So when you're out of 5, you're done. So when you're out of 5, you have to turn everything in on time because you can't write yourself an extension any longer. I can tell you right now, these bonus days are worth much more later in the quarter. Do not use bonus days on Project Zero. Project Zero should take you 10 minutes. It is not worth vacationing for 48 hours and then doing Project Zero and blowing 2 bonus days on an easy project. Okay, save them if you can, but that's what they're there for. They're there so you can manage your life a little bit easier. Again, they are not here to enable you to take 2-day procrastination vacations. They are here to help you succeed through your conflicting priorities. And you're just feeling sick some morning. Okay. But please, please do not use them up early. Not 0, not 1, not even 2. Save them at least till after project 2. That's my advice. Okay. To use one, you don't actually need to let me know. You don't need to ask. You just have to turn it in late. I have a script that'll go out and look at all of your turn in dates and will tell me this person gets 1 bonus day deducted, this person gets 2 deducted. And then I keep a spreadsheet. It's up to you to keep track of your bonus days, but if you do lose track, just send me an email and I will tell you. Also, after every project's turned in, I'll run a Python script that emails you and tells you how many you used up. Okay, there are some really silly things you can do to lose points on your project. Don't put your name on the first page, -5. You didn't turn in a PDF. You turned in a docx or something else. Our script looks for PDFs. Okay, if you do this, we're not going to be able to find your turn in, -5. Eventually we'll find it because you'll probably tell us, but -5. You put your PDF in a zip file and thus we could not get it with the script, -5. Anything that causes me to have to go back and rehandle your submission, -5. Okay, turn it in right the first time and there's nothing to worry about. But these are ridiculous ways to, at your age, to lose 5 points, but some people will anyway. All right, virtual machines. Our experience in this class with virtual machines has not been good. I don't think they are automatically set up to do multi-threading. You can try and use a virtual machine if you really, really need to, but if you start getting really weird results, don't. And stop doing that. One other thing, if you're on the Linux systems, like Flip, but you've used a Microsoft Windows program to edit your file, sometimes Windows editors will put an extra character at the end of each line. And Linux interprets that as a garbage character, something that's to be flagged as an error. Well, if that happens, there's a couple ways you can do this, but here's what I recommend. There's a program built into Linux called DOS2 Unix. You bring in this file, it removes that junk and outputs it to this file. Okay, now, sorry about this. This is a fact of life when you're mixing Windows and Linux systems, which a lot of times in these classes we are. I just thought you'd enjoy this. This is American history. Admiral Grace Hopper, who's very famous in early computing, she was programming something and it wasn't working. And this is back when computers had mechanical switches and relays in it. And she got into the system and found a real live bug there, like a real bug. And so she pulled it out, taped it into her lab notebook, and documented it, like a good software engineer should. Well, this bug and her comment is now in the Smithsonian Institution. And so, since you are all experts on debugging software, I thought you would enjoy this. Okay, software bugs in history. So there we go. There is what you need to know to succeed at turning in the projects. So go do that.